So today's lecture is on combinational logic or combination logic. So what we're going to look at in today's lecture, we're going to look at basic logic gates, and then we're going to look at Boolean operations and expressions, and then laws of Boolean algebra, and then there's a theorem called DeMorgan's theorem, which is important for this digital electronics. And then we're going to look at universal properties of NAND gates and NOR gates. And then we're going to look at some basic combinational logic circuits using NAND gates and NOR gates. Okay, so there are the subtopics that we're going to cover in today's lecture. The learning outcomes from this lecture. Okay, so the requirements at the end of the module, what you need to know, you need to be able to describe the operations of digital logic gates. So the digital logic gates that we're going to look at is NOT gate, AND gate, NOR gate, NAND gate, NOR gate, OR and XOR, exclusive OR, and exclusive NOR gates. Okay, so these are the basic gates of digital electronics that you're required to know. And what it means to describe the operations means that you need to know the truth table, the gate symbols, and the Boolean operations. And then you also need to know how to apply basic laws of Boolean algebra and the DeMorgan's theorems to digital logic gates network. Okay, and what that means is you need to know how to do Boolean simplifications. So you're given a Boolean algebra or a large logic circuit, you need to know how to simplify them. Okay, so that is the requirement that you need to be able to grasp from this topic. So let's dive into the topic itself. Okay, so I'll start off with what is logic. So from binary signals, logic can mean true or false, on or off. And in digital electronics, it's high or low, and that can be associated with a voltage, either plus 5 volts or high, or 0 voltage or low. So instead of using high or low, we also use 1 or zeros as the logics level for digital electronics. Okay, so logic 1, we have a positive voltage. Logic 0, we have 0 voltage. That is the normal definitions that we use in digital electronics. Logic circuit can be divided into two. So we have the combinational logic, which is the one that I'm covering with you. And then we have sequential logics. So what we have is that we have a set of inputs. So we're putting the inputs 1 or 0 into the circuit, and then we expect some outputs coming out from the other end of the circuit. So we have a combination of logic gates here, and then they're going to give us some output on the other side. Okay, so this output doesn't influence the outcome of this circuit. Okay, so it all depends on what the input is, and that is what it meant by combinational logic. A sequential logic, so what you have is that you have a set of input, and then the output is fed back to the input. So it means that the output not just depends on the input, but it also depends on the output itself. So it is actually the time-dependent sequence. So we said that the next stage depends on the previous stage. So let's say t equals to 1. I have this set of output. Let's say and then the next time interval, the output depends on Q3. So Q3 is become the input of the circuit, and that has an influence of the next set of outputs. So these are sequential logic. So in a way, the circuit has some form of memory. But we're not dealing sequential logic at this part of the module. That will be dealt with in the next or the last 7 weeks of this semester. Okay, so for this part, we're purely looking at combinational logic. It means that the output is only depends on the inputs. Okay, so the output has no influence to the outcome of the circuit. Okay, so this is a summary of what I said. So combinational logic has no memory, so it doesn't depend what the output is. The state can only be 2 values, so this is either on or off, true or false, a high or a low voltage. Okay, so it's a binary system, only takes 2 values. Boolean logic, that can be referred to as Boolean variables and Boolean algebra. So it's very similar to your mathematical algebra that you learned. You can have variables such as x, y, and z. Similar applied to Boolean logic. And it can be manipulated with a set of laws. Similarly, you have a set of law when you manipulate your normal algebra. Okay, but here we're going to learn a set of law that is related to Boolean algebra. So in digital electronics, the Boolean variable are represented by voltage, a high or a low, or 1 or 0. Or in terms of voltage, it will be 5 volts or 0 volt. So Boolean functions, just like your normal mathematics, let's say in math, we said f of x is equal to, let's say, x squared plus 2. So this is our functions, and this is our variable. So our function dependent on x in our normal mathematics algebra. In Boolean algebra or Boolean functions, again, we have a function f, and then we have the variable or a Boolean variable. Okay, so this is the 2 variable that the function depends on. So in other words, a and b is the inputs of our Boolean functions or our logic circuits, or a combinational logics. And the function f of a and b will be the output of our Boolean, or the output of our logic, combinational logic. Okay, so logic gates allows the Boolean variables to be combined. So we can manipulate the variable by using logic gates. The three basic logic gates are NOT gate, or we call it inverter, and then AND gate and OR gate. So these are the three basic gates. And then AND gate, we have its variations, such as we have the NAND gate, and then OR gate, we have the NOR gate, we have the exclusive OR gate, and then the exclusive NOR gate. Okay, so these are the variations of the original basic gates, such as AND and OR. So in actual fact, there are only three basic gates in digital electronics. Okay, let's look at what are all the individual gates. So NOT gate, or the inverter. So the functions of a NOT gate, we have the functions. The input is A. So the functions or the Booleans has an output called A bar. Okay, so there are many different variations of writing this. So the one that we're going to use here will be A with a bar on the top. So we call it A bar. In words, you can set not A, or other way of expressing it will be A with a dash, or we call it A complement. Okay, so you'll find some books who use this symbols, but here we're going to adopt the A bar symbol. Okay, so the logic gate symbol will be a triangle with a bubble in the front. Or sometimes we have the bubble at the back. Okay, so there are two ways of drawing this symbol, but this is the more common one. So sometimes it's drawn this way. It's purely due to the actual practical circuit. We call it the active input. So it means that if the input is active high, then we don't draw a bubble at the input. But if the input is active low, then we draw a bubble at the input instead of the output. Means that active high means that by default, I don't put an input to the circuit, the input is high. Okay, so when you power up the inverter, if you try to put a multimeter to measure the input, you measure that there is some voltage at the input, and the output will be automatically low, or 0 voltage, for example. In this case here, it means that the input is active low. So it means that you power up your inverter, there will be no voltage at the input. And if you measure the output, even though you don't put an input, the output will be high. You get a voltage coming out. The truth table. Okay, so truth table is very important in digital electronics. Basically, it tells you all the different combinations of the logic. Okay, so the truth table tells you basically what are all the different combinations this gate can have. So meaning that A is my input. So if I put an input to my inverter, okay, so binary, so the input can only be 0 or 1. Okay, so if I fill up the input with 0 and 1, there are the two possibilities. And what are the outputs I can achieve from this circuit? So my output, f of a, so if I put a 0, then my input, I'll get a 1 at the output. Okay, so I fill up this table, input 1, a is 1, the output, which is the f of a, now input is 0, output f of a will be equals to 1. If I put my input as 1, then my output will be 0. Okay, so that are the two different possibilities of this circuit, and this is called our truth table. So NOT gate has the output opposite of the input. Okay, so if I put a 0, the output will be 1. If I put a 1, the output will be 0. Okay, so it do exactly opposite to what the input is. Because the input only two possibilities. So if it's 0, the output is 1. If it's 1, the output will be 0. Okay, so the A bar is the inverse of the inputs or the complements of the input. So that is the NOT gate. OR gate. So in the Boolean algebra, the operator we use for OR gate is the plus sign, which is the plus sign that you use in your normal algebra. So my input is A and B, and then the operation is OR, and the algebra or Boolean algebra operator for OR is a plus sign. So this is called A or B. The logic gate symbol for an OR gate, you have the inputs. So here I will draw two inputs, A and B, but your OR gate, there are some OR gate can have more than two inputs. So basically the gate is a curve at the input and then a pointed at the output. Okay, so input can have many inputs, but in this one here, of functions of Boolean is just a Boolean variable is just two, A and B. So there are two inputs and one output. Okay, so this is our symbol for our OR gate. And then the truth table. Okay, so because we have two Boolean variable, A and B, so now the possibility of all the inputs will be 4 different combinations. Okay, so basically you're going through your binary number system. So this will be 0, 1, 2, 3. So this is the equivalent in decimal number. So if you go through the value from 0 all the way to the maximum possible combinations of binary number, then you will have covered all the possibility of the logic. Okay, so the truth table, when you want to draw a truth table, You have to go through all the different combinations. So the best practice is to count from 0 to the maximum number, which is 2 to the n. And here, n is the number of Boolean variable. So in this case, it's 2. So it's 2 to the n minus 1. Okay, so this will be 4 minus 1. And therefore you count to 3. So for example, if you have 3 variables, A, B, C, so again you start from 0, 0, 0, 0, 1, all the way to 1, 1, 1. So basically you're counting from 1, so 0, 1, 2, all the way to 7. And in this case, you have 8 combinations. So again, this is 2 to the 3 minus 1. Okay, so that is so the first thing to draw a truth table, you want to list down all the possibility of the inputs, and then you look at the output. So the OR operations. So if one or both inputs are at logic 1, then the output will be logic 1. Okay, so either one of the inputs 1, the output will be 1. Okay, so if I go through my truth table, so 0, 0, so no ones in the input, the output is 0. 0, 1, so one of the inputs is high or is 1, the output is 1. 1, 0, and then the output will be 1. And then 1, 1, then the output will be 1 also. So it doesn't matter if both input is 1. So all we care is either one is 1. So if both is 1, that is fine as well. Okay, so that is our OR gate. So I'm sure you have saw these combinations in your lab last week. Okay, so when you test out your circuit, I'm sure you have come across this sort of combinations when you switch the input on and off with these combinations. AND gate. Okay, so the expressions or the operations, the Boolean operation of an AND gate is a dot, similar to our algebra. We said x times y in normal algebra. So here times multiplication, we use a dot. Here n in our Booleans, we use a dot as well. And this is quite fitting in this case here. You can think of this dot as a multiplication of 2 variables in your normal algebra. Okay, so an AND gate, the symbol, the input has a flat line, and then the output is a curve. Okay, so compared to our OR gate, the input is curved, the output is pointed. Okay, so AND gate is flat at the input and a curve at the output. So here the logic of an AND gate. So we need both inputs to be a logic 1. And then we get an output of logic 1. Okay, again, we go through our truth table. So if 0, 0, so both input is 0, then our output is 0. If A is 0, B is 1, the output is also equals to 0. So this is similar to your normal algebra. So if I take 0 multiplied by 1, that is also equals to 0. Okay, so similarly here, 1 multiplied by 0 will give us 0 also. And here is 1 multiplied by 1, this gives us 1. Okay, so in AND gate or AND operations, that will be the same with your normal multiplications. So you're multiplying the two inputs. Okay, so this is the truth table of an AND gate. So this is its variation, NAND gate. So in actual fact, you only need to remember the logic of an AND gate, which is the basic gate, and you should be able to derive the truth table of the NAND gate. So the NAND means not AND, or negate of the AND. So the Boolean functions of a Boolean variable A and B, so it's written at this way. So A and B with a bar on top. So it's called AB bar, or not A and B. Okay, so this is called a NAND gate. So the symbol of our NAND gate is our AND gate with a bubble at the front. So as we can see that earlier on in a NOT gate, the bubble tells us that that is the inverse of the input, or inverse of the logic. So here we have an AND gate putting a bubble in the front that makes it not AND, or we call it a NAND gate. So the truth table, okay, so this is the truth table of our AND gate, which you just see just now. So the negate of AND, or not AND, which means that it's the complement of this logic here. So meaning that if I have a 1, or if I have a 0, it will be a 1, 0 will be a 1, and if it's a 1, it will be 0. Okay, so that is our NAND gate. So in simple term, in words, the output is logic 1, except if both inputs are logic 1. Okay, so it will be 1 all the time, except when the two inputs is 1, then the output will be 0. And then the NOR gate, which is not OR. So the Boolean expressions of that will be our AND with a bar at the top. So this is called A and B bar, or not A or B. Again, the symbol is our is our OR gate symbol with a bubble in the output. So this is the truth table of our OR gate. And then the NOR gate is the inverse of that. So when we have a 0, it will be 1. If it's a 1, it will be 0. So here, the output is logic 0 most of the time, except when both the inputs are 0. Then we have a 1 logic, the output. So is that clear about all? So these two are called universal gate, NAND gate, and NOR gate. We're going to look at why is it called universal gate in a few slides later. So this is a derivations or a variations of an OR gate. So the base gate of this is an OR gate, and the NOR gate is just the inverse of the OR gate. And then we have what we call an exclusive OR gate. Here I use EX, but very often it's just XOR. Okay, we don't normally E is not put down there, so normally just XOR, and this is exclusive OR gate. The operations of this, or the Boolean operator for this, is our plus sign with a circle around the plus sign. This is called an exclusive OR. So there is no equivalent operator in our normal algebra. So this is a special operator that is used for exclusive OR. So it's called X OR B. So A XOR B, A exclusive OR. So the logic symbol here, again, is derived from our OR gate, and then with an additional curved line at the input. And this tells you that this is an exclusive OR gate. And the truth table of this, when both input is the same, the output is 0. Okay, so when both input the same, the output is 0. So it doesn't matter if it's 1 or 0. If both the inputs are the same logic, then the output will be 0 or low. Okay, when both input is 1, output is low. Compare that to our OR gate. Our OR gate, when both input is 1, is still 1. But in this case here, exclusive OR, when both input is the same, both input is 1, the output will be 0. So output is logic 1 only if the inputs are different. Okay, so the input is different, meaning that one input is 0, the other one input is 1, then we have an output of high or 1. And then we have the XNOR, or the not exclusive OR, and that will be the opposite of this. Okay, meaning that if I were to draw out the truth table, or the operation of that will be, so not exclusive OR, we'll put a bar on the top, then the output will be the inverse of this. So meaning that when both inputs is the same, then the output will be high, equal to 1. And if the inputs are different, then the output will be 0. Okay, so that covers all the gates that you need to know in digital electronics. So that is the foundation or building block of your combination logic. So this is the base, and you need to know all the truth table of all these individual gates. And then when we combine them, then you can derive what are the outputs of the combined logic. So very important that you learn and memorize all the different truth table of all the different gates. Okay, so if you know all this gate truth table, then you have a sound foundation in digital electronics. So there's no way or no other way to this except to remember the truth table. Okay, you have to learn that by heart. So in actual fact, you only need to learn 3: the NOT gate, the OR gate, and the AND gate. And the rest is a derivation of this. So NOR gate is the inverse of the NAND gate is the inverse of the AND gate, and the NOR gate is the inverse of the OR gate. And then exclusive OR, in this case, you have to learn, or you have to remember a little bit more that if both inputs is the same, then the output is 0. And then the inverse of that will be your exclusive NOR gate. Okay, so that is your logic gate. And the next, we're going to learn about the law of Boolean algebra. Okay, so the first one, the laws of 1 or 0, is basically the gate that we talked about just now. Okay, so not 1 with a bar, there will be 0. Not 0, so 0 with a bar will be 1. And so we can think of this as multiplications. 0 times 0 gives us 0. 0 times 1 or 1 times 0 gives us 0. And then 1 times 1 gives us 1. And then O, the symbol looks like an addition. So here, the first two is it's okay, it's just basic addition. 0 plus 0 equals to 0. 0 plus 1 equals to 1 plus 0. And that equals to 1. Here is not the normal additions that you know. So 1 plus 1 still equals to 1 in our Boolean algebra. Okay, so it's not equals to 2 or equals to 1, 0. So here is a Boolean algebra. So this is not equals to 1 plus 1 equals to 1, 0 in your digital addition. Okay, it's not. So 1 plus 1 in Boolean algebra is 1 plus 1 is equals to 1. So that is your OR operation. And then special property of 1 and 0 is one of the Boolean variable is x. So x is varying. It can be 0 or 1. So this special property tells us that in AND, doesn't matter what x is, if I AND x with a 0, they're going to give us a 0. If I AND x with 1, then it's going to give us 1. Okay, so the output is purely depend on the input. If I AND with a 1. If I AND with a 0, it doesn't matter what the input is, the output is always 0. In OR operations, if I OR with a 0, then the output depends on the variable x. If I OR with 1, then it doesn't matter what x is, the output is always 1, or always high, or always true. Okay, so this is a special property. If you AND with one logic that is constant, okay, either 0 or 1, and that is the outcome. of it. The third one, the third law, is called idempotence law. So if x and with x, that's going to give us x. And x and with x, no. So x and with x going to give us x. And x or x is going to give us x as well. Okay, so doesn't matter what operator, if the two inputs is the same, the output follow what the input is. Okay, doesn't matter whether it's an and or, if both inputs are identical, then the output will be the same as the input. The fourth one is called complementary law. Okay, before I go any further, okay, although I put all the name here of the different law, I'm not so concerned about you trying to remember what's the name of the law, but what I want you to remember is the property of the law, so that you can make use of them to simplify Boolean algebra. Okay, so I would not ask you what's the name of this law, for example. So you don't really need to memorize the name of the law, but you just need to know the property of all the different laws. Okay, so this is called complementary law. So it means that x and with x complement, that's going to give us 0 all the time. In involution's law, so if we double complement x or double complement any Boolean variable, we end up with itself. Okay, so if we inverse x and then inverse again, then it will become back to itself. Okay, so that is the fifth law. And then the sixth one is called commutations law. So this is basically the same as your normal algebra. So if we swap our variable around, whether it is and or all operations, it's the same. It doesn't make any difference. So it means that if I put x first or I put y first, it doesn't really matter. Same thing here for our all operations. So in terms of logic gate, goes for the fifth one, meaning that if I put x, y through my AND gate, it's the same as putting y next to my AND gate. Similarly for an OR gate, and that's the same. I think some students asked me about this in the lab last week. So does it matter which pin do I put, A or B? Okay, so it doesn't matter. So this is the law that tells you that it doesn't matter which way around you put the input. And then the seventh one is called associations. So again, this is the same as your normal algebra, multiplications. So it doesn't matter where I bracket my two variables, is the same. Same thing for all operations. Okay, so I can do my y and with that, then n with x is the same as if I n x with y first, then z. Okay, so to put it to perspective, so what it means of this law is that if I do y, z, n of that, and then n with x is the same as doing x, y, and with a z, and the same for OR as well. Okay, so if I replace all this with OR gate, that will be my OR operations, and that is the same. Distributions law or distributive law, there are two. First one, so if x and with y or z, this can be expanded just like in your normal algebra. So here we can expand it, which is x times y, x times z in your normal algebra. So here it will be x and z, or x and z. Okay, so this is your first distributive law. The second one, okay, so x and with y, no, x or with n, sorry, let's do this again. X or with y and z. And this can be distributed into x or y and with x or z. Okay, so this is not so straightforward. It's not so what I'm trying to say is that it's not so straightforward that you can see and identify that. I will come back to this in the next slide, or maybe I do that and then come back to this, to the 9 one. Okay, so to prove that point, okay, so my second distributive law, so we have x and with y or z, and the law said that it can be distributed in this fashion. Okay, so to prove that, we can go from this side to show that this is equal to this. So we can do our normal multiplications like your normal algebra. Okay, so we times x with x. Okay, we get x and x. So we do this. And then we do this. Okay, so.
Yep. Rene ada apa? Oh, selesai.
Is there a question somewhere?
Sorry, sir. I accidentally to press pass.
Okay, there's no worries. So if we distribute this, so we got x and x, and then all with x and z, and with x and y, all with y and z. And if we applied one of our earlier law, so we said that x and with itself is equals to x. So here we simplify to x. I miss out something. Okay, so this is yn with z. Okay, so this is basically from here, just simplifying x, n with x equals to x. So this is basically this term here, just swap it around. Okay, so that when I write this, I can collect my term x. So we have common terms here, x, x, and x. So we can collect all the x. And then here will be 1, all with y, and all with z. Okay, and then another theorem from earlier on said that anything all with a 1 will give you 1. So here, x all with, no, xn with 1, all with 2 variables. And this thing here is going to give us 1. Okay, and then x n with 1, that is going to give us x. Okay, again, this is one of the law earlier on. And therefore, this end up with x all with y and z. Okay, so this proves this second point of our 8th law. I am lecturing. Yeah. Okay, so the next one is absorption's law. So the first one, x all with x and y, and that is equals to x. And then the second one is x all with not x and with y, and that is equals to x or y. Okay, again, to illustrate that, so the first one, so we can collect the term x, which is common. So we can write down x, which is common, and that will be 1 all with y. Again, here, anything all with 1, it will be equals to 1. And then x all with 1, and that's going to be equals to x. Okay, so remember I said I don't really interested for you to know what's the name of all this law, but you need to remember the property. So it means that you need to know that 1 or with something is equals to 1, but what is really core of this law is not really important to me. Okay, so all you need to know is that you know this property, or for example, this property here, x n with 1 is going to be equals to 1. But what actually this law call is not of importance. Okay, so that's my point that I mentioned about the name of the law. And then the second one, so x n with not x, no, x all with not x n with y, and that will be equals to x or y. So if we use the first one, the first of this law, okay, meaning that if I use this as my starting point, okay, we show that x or x and y we know that this is equals to x. Okay, so here we know that this thing here is equals to x. So we can expand my x here. Sorry, there's a mistake here. Okay, so my x here, using the first law, we can expand this into this. Okay, so that is from here. So x is equals to x, or with x and y. So we expand x into this, and then this is same, okay, from here. And then we can collect the common term for y. So we have a common term of y here, and then we can collect that term. And then we have x or with y that end with x or with complement or the inverse of x. And then from an earlier law, okay, missing. So x or with its complement will be equals to 1. And therefore, we prove that these terms here, this terms here is equals to x or y. Okay, so that's how this law come about. This is called DeMorgan's theorem. Okay, so x nan with y. Okay, so the complement of x and y, and that's equals to the complements of x or with the complements of y. There are two laws. One governs, so this is nan, and this is no. Okay, so for no, that will be equals to the inverse of x and with the inverse of y. Okay, to remember this is a statement here to help you to remember this DeMorgan's theorem. So if I have a solid bar, okay, what I do is I break the bar, and then I change the operator. So I end up with x with a bar on itself, y with a bar on itself, and then the operator change from n to o. Similarly for the second one, I break the bar and then change the operator. So now the bar is broken, and then the operator has become from o to n. Okay, so this is called the DeMorgan's theorem. And this is a very important theorem that you need to know for digital electronics. Okay, so things to remember again, if I have a solid bar, I break the bar, change the operator. Break the bar, change the operator. Okay, so go from n to o, and then from o to n. And that's DeMorgan's theorem. The significance of this, if we look at the first one, which is the nan operator, Okay, so if I complement both sides, so I'll start off with this, and I complement on both sides, I inverse it both sides so that my equation is still balanced. So if I make left sides inverse, then I make the right side inverse as well. Then I maintain my equality. Okay, so again, applying one of the law, so a double inversion, it will back to itself. Okay, so I inverse and then inverse again. So in this case here, it became x and y. And then you can see that on the right hand side, this has become x, or the complement of x, nor with the complement of y. So here we are changing an AND operations to a NOR operations. Okay, so from one side we have an AND functions, and the other side we have a NOR functions. So we can implement an AND functions using a NOR gate. So in terms of combination circuits, so start off with is on the left hand side we have x and y. So we have an AND gate here. Okay, we can implement that by inverse x, inverse y, and then NOR them together. So here, putting my x to an inverter, I get x bar, y to an inverter, I get a y bar, and then x bar and y bar will be the input to my NOR gate, and what I end up here will be x bar, y bar, 4, and then whole thing inverse, and that's equals to our AND operations. And we can build this using purely just NOR gate. Okay, so meaning that if I time my inputs of x and put it through a NOR gate, I also get an inverse of that. And here is the inverse of y. So you can see that an AND gate can be implemented using just NOR gate. Similarly, you can do the same for all functions, and you can implement it using NAND gate by applying DeMorgan's theorem. Okay, so that leads us to what we call a universal gate. Okay, so NOR gate and AND gate, NAND gate, is called the universal gate. So basically, why is it called universal? Because you can construct any circuit functions using either NAND or NOR gate. Okay, so any circuit function can be implemented using purely just NAND gate or purely using just NOR gate. Okay, from practicality point of view, so if you are not so manufacturer, I mean, if you are prototyping circuit, if you are a company trying to design logic circuit, so it is cheaper to buy your gate in bulk. Okay, so you can stock up a lot of NAND gates, or you can stock up a lot of NOR gate. You can decide which one you want to do, and that's all you need. You don't need to buy inverter. You don't need to buy AND gate or OR gate. And if you buy in bulk, it will be cheaper. Okay, so then you can design any circuits, any functions using the NAND gate that you have. So if I choose to stock up just NAND gate, I can build any circuit. I can prototype any circuits using just the NAND gate. Okay, and that made prototyping cheaper. Okay, so that is from the practicality point of view. Okay, here's an example. Okay, how we can construct a truth table. So here we have Boolean functions that is not A and with not B, or with A and B. So if I want to work out what is the truth table of this combined Boolean expressions or combined logic, so I start off with all the combinations of A and B. Okay, again, I mentioned this early on, so all you need to do is you count from 0 to the maximum here, which is 3, which is 2 to the 2 minus 1. Okay, that gives you all the combinations. So you can see that these combinations of logic has an A bar, a B bar. So best practice to work out the truth table. So you work out the intermediate logic. Okay, so in this case here, I got my A bar. So A bar is the inverse of A. So A is 0, here we 1, 0, 1, 1, 0, 0. And then my B inverse is when B is 0, 1, 0, 1, 0. And then next stage, I have an AND of the two inverse of the Boolean variable. So means that will be these two columns. So A bar, it AND with B bar. So 1 AND with 1. So 1. Okay, so remember I said that you need to by heart the truth table of the basic operation. So you need to know the AND truth table by heart. So 1 and 1 give you 1. So 1 and with 0 give you 0. And then 0 and with 1 give you 0, 0, 0, give you 0. And then the next one, A and with B. So this is my two variables. Okay, 0 and with 0 give you 0. 0 and with 1 give you 0. 1 and with 0 give you 0. And 1 and with 1 give you 1. And then the whole operations, which is my functions here. So that depends on these two columns. Okay, so this is now an OR operations. So 1 OR with 0 give you 1, 0, 0, 0, 0, and then 0, 1 give you 1. Okay, so that is how you build up your truth table if you have a combination logic. Okay, so always good idea to work out all the intermediate state and then work it out from left to right until you end up at the Boolean functions or the output of the combination logic. So this function is an XNOR, which means that is the inverse of the exclusive OR gate. Okay, remember our exclusive OR? either one of the inputs is 1, it gives you 1. If both inputs the same, give you 0. Okay, so that is our exclusive OR, and this is the inverse of the exclusive OR. Or we call it complement of the exclusive OR. Okay, so we can, in terms of combinational logic, we can easily build this circuit with inverter, AND gate, and OR gate. Okay, so here we have our two input variable, A and B. Put through an inverter, we get A bar, B bar, and then put that through an AND gate with A bar and with B bar. And then we have our A and B, here will be A and B. And the outputs will be A bar, B bar, and with A, B. So remember we said about universal gate. So if you want to build this logic using just NAND gate, how do we go about doing that? Okay, so we apply DeMorgan's theorem. So we have our original Boolean expressions. So we applied, so if we inverse it and then inverse it again, we're back to be self. Okay, so we do a double inversion that is the same as this original expression. And then we can apply DeMorgan's theorem. So remember, as we said that we break the bar and we change the operator. Okay, so this is equals to, so the top bar still there, okay, maintain the top bar. So break the second bar. Now we have okay. So now we have a NAND operations. And now we can build this circuit using NAND gate. So again, we have A, and then B. Okay, I have to draw that. I have it here. So we have A and B. Okay, so inputs are tied. So what I get here is just an inverter. This is A bar. This is B bar. And then I do a NAND operations. So this is A, B. This is a NAND operations. And then my A and B variable. So here's still A, and this is still B. And then here is A inverse of A and B. And then here is the NAND of these two inputs. So we have our original expression, which is A bar, B bar plus AB. Okay, so we implemented the exclusive NOR gate using just NAND gate here. Okay, so as I mentioned, you can build any circuit using just universal gate. So here we show that we build it using NAND gate. The other things that you need to understand that your logic circuit doesn't just depend on discrete logic at the input. Sometimes the inputs can be time changing. So for example, if the input is some form of a waveform, then the output will be changes with time. Okay, so for example, if my input A at, let's say, if this is my time axis, let's say this is my starting time, time 0, let's say nanoseconds. Let's say here is 1 nanoseconds, 2 nanoseconds, 3, 4, 5, and 6. So which means that my input changes every 1 nanoseconds. So similarly, my output of my combination logic will change every 1 nanosecond as well, depending on how the input change. So for example, so this is my the previous circuits that we have just now are exclusive NOR gate. If my input is performing in this fashion, changes in this fashion, and my B input is changes like this, then my output will be changing with time as well. And how do you work out the outputs in a timing diagram? So one way to do it is to write down the logic at the waveform. So here will be 1, 1. So write down the logic for every time frame. So all this we call a one time frame. This will be 0, 0, 1, 0. Okay. So there's my A. Then my B is 0, 1, 1, 0, 0, 1. And then you can refer to the truth table. Okay, so in this case here, this is my truth table. So 1, 0, okay, 1, 0. 1, 0 give us 0. So we got 0 here. 1, 1. Okay, 1, 1 give us 1. So we got 1 here. And then 0, 1 give us 0. 0, 0 give us 1. 1, 0 give us 0. And 0, 1 also give us 0. And then 0, 0 give us 1. Okay, so we can draw out the outputs of this logic frame by frame by referring every frame through the truth table. Okay, so we can fill up the timing diagram of the output in this way. How about this? Okay, when it gets more complicated, so circuits, so this is a combination of logics. So again, we can look at it at stage by stage. So I got my A, if I call this, so this is my A bar. So I can start working out A bar. So again, fill up all my time frame. So when this is, so this is 1, 1, 0, 0, 1, 0, 0, 1, 1, 0, 0, 1. Okay, when A is 1, the inverse of that will be 0, 0, and then 1, 1, and then 0, 1. And then B bar, again, is when it's 0 is 1, when it's 1 is 0, Then we have A bar and B bar AND. So meaning that this is now is 0, 0, 1, 1, 0, 1, 1, 0, 0, 1, 1, 0. So n of these two. So 0, 0 going to give, not 0, 1 going to give us 0, 0, 0, 0, 1, 0 going to give us 0, and then 1, 1 give us 1. Then this gives us 0, and 1, 0 give us 0. And then A and B. So we look at the top one. So here 1, 0 give us 0, 1, 1 give us 1, and then 0, 1 give us 0, 0, 0, then 1, 0 give us 0, then 0, 1 give us 0. And then we OR the two. So we OR this, this, and this. So we have 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 0. Okay, so the final expressions, that would be 0. We got 1 here. We got 1 here, and 0. Okay, so that's how you build up your timing diagram. You look at every stage, and then you draw out the timing, and then you can work out the final expressions. Okay, so not sure whether I've done something wrong. I might have. But anyway, what I'm trying to show you is how you go about to working out the timing diagram for a combinational logic. Okay, so no, that's correct. Okay, that's fine. Yeah. So that is on timing diagram. Also something you need to know. It's quite simple on combination logic because it's all just depend on what the input, and then you derive the output timing diagram of the circuit. It will get a bit more complicated in sequential logic. When I say complicated, it doesn't mean that it's very difficult. It's just that you have to consider the input, the output as one of the inputs. Okay, so you need to feed back the output back to the input. So I'm going to end this lecture with some simple applications of the basic gates that we have looked at. These are all applications from our recommended text. So one of them is the seatbelt alarm system. Okay, so what you have there is that it's a simple AND gate operation. Okay, so when you start your car, for example, okay, ignition switch. When you start the car, when it's on, it will be high. And when the car is off, then it will be low. It's off, it will be 0. And if you haven't buckled your seatbelt, it will be high. And when you buckle a seatbelt, it gives you a logic low. And those signals will fit into an AND gate. And then when you start your car, there's a timer, for example, the timer time for 30 seconds. So it's high for 30 seconds when the ignition is on. And then it determines whether So you have a high, and then you have a high here, and then it purely depends on whether a seatbelt is buckled. So if it's high, if it's not buckled, so all three signals is high. So I got 1, 1, and 1. So I give you a 1 here, and that will trigger an alarm circuit. And then you hear a warning telling you that your seatbelt is not buckled. But the moment you buckle your seatbelt, this go to 0. So you have 1 and with 0, and with 1, then the output will be 0. Then the alarm will not sound. Okay, so when you buckle your seatbelt, then the alarm circuit is switched off, deactivated. Okay, so this is one simple application that you can use an AND gate for. Here is an OR gate in operation. So this is an intrusion detection system. So for example, your home alarm system, for example. Okay, so you have many different sensors. Let's say this is your door. So if your door is closed, then it will be low. If the door is open, then the sensor gives you a 1. Or you have 1 as your at the window, let's say. And then maybe you have your EIR sensor, so your motion sensor. Similarly, if there's a movement, that's going to give you high. And then if there's no movement, give you 0. So it means that any of this sensor is triggered, then your alarm circuit will be triggered. Okay, so for example, someone break into your house through the door, this become 1, even though this is 0, it's going to give us 1, and the alarm will sound. So if someone break the window, then this will become high, and then the alarm will sound. Or someone get into your house, even though without going through the door or the window, but it's moving around inside your house, you got a passive infrared sensor that detect the movement, and this become high, and then that will sound the alarm circuit as well. Okay, so simple OR gate in operation. A NAND gate, for example, here we have a level sensor detecting the liquid inside a tank, for example. So when there is liquid, then the sensor gives you a high, and then the output will be low, and therefore your LED here will be on. So we have a current flow down this path. So when the, let's say tank A, water level drop below the sensor, then this turn low, and then here turn high. So we have plus voltage and plus voltage, and therefore I equals to 0. Based on no current flow, and therefore the LED doesn't turn on. It's not biased, and therefore the green light turn off indicated that either one of the tank has a water level that is below the sensor, for example. Okay, so that is some simple applications of how gates are used. Okay, with that, I'll stop today's lecture here.